What homework? See, if I can even find the listing of what's due, you had to do a influence analysis of the property evaluation data, and you had to do a couple of problems out of Chapter 7 involving second-order polynomial fit, test for lack of fit. Okay, does the interaction term contribute significantly? So it's basically doing some S statistics, which is good practice. We can go over that solution for the the quiz that we're going to have tomorrow. So that's a good practice question. And then 711, that's basically a redo of your test problem. So I can go over that today if you want. You could have done your problem that way. 711. The spline problem. Yeah. Yeah. So there's a number of different approaches to your problem 4 on the homework, on the test. Okay. And the easiest way is just to apply the theory you now know about splines. I don't know. Did some of you do it that way?
I started it that way, but I didn't understand the problem going down, so I went back.
You went back in the old way.
Mm-hmm.
Okay.
I think it's the second part. I mean, I knew exactly where you were reduced that down, and you had little things there about 3 columns instead of 4. I got the first part just fine.
Yeah, there was a number of ways of doing it. I mean, you didn't. The answer to X is not unique in the exam problem number 4. Okay, it's not a unique answer to X, but it certainly has to have 4 columns in one case, 3 columns in the other.
Okay.
Because either 4 parameters or 3 parameters in the model. Okay. Okay. So it have to. That's the only thing that was true about the statement of the problem. But it turned out to be easiest to do by the method of 711. Okay. Maybe we should go over that a little bit right now. I'm going to not use the computer today. It looks like. Might as well turn this thing off. Turn this thing off. I think we can get by without it. I have enough stuff in the notes that I'll just hand you the notes and we'll work off the board. Okay. Probably an overhead would work, but I could do it after the break. Yeah. I could just get the overhead copies after the break. Those are the tests? Okay. Yeah. All right. Shane turned in his already. He's not able to be here today. So let's look a little bit at what is the spline model for this case of fitting a straight line, a couple straight lines. Either this business. This is the reduced model. Okay. Okay. Slope changes. And this is a reduced model where the spline is continuous. This is on exam 1, number 4, and problem 711. Reduced model in the exam, anyway. It's not clear what they want in problem 711. Okay, what the full model is. Okay, let me see. Piecewise linear regression doesn't say continuous. Okay, so I'm going to assume it's the same business. Okay. Piecewise linear regression model should be fit to these data. Okay. So does he want a continuous one or not? Let's look and see if there's any hints in the book what he suggests to be done with that. Here he has the piecewise linear regression. Okay, and he has the general case of the discontinuous one. All right. If x is less than t, and then if x is greater than t, then the straight line model is this. Okay? the regression function is shown. Note that the parameter b10 represents the difference in mean response at the not t. Okay, so this is the reduced model. The spline is continuous. In the full model, is basically you got a function like this, where there's now a jump. It doesn't have to be a positive jump, but there's a different slope, and there's a discontinuity here. Okay? This is the not t. This is a function. Okay, this is t. This is the function of x. Okay? This is y. So this is the spline is continuous, and here is the general piecewise linear spline. So he's the reduced model in the exam. This is not. There is no reduced model in problem 711. They're not asking for a reduced model. They're saying you've got this thing. Well, actually, the reduced model is reduced model in problem 711. And the reduced model in problem 711, here's what it is. Is that you've got this line, and then you've got another line parallel to it, but with a discontinuity. Okay, the slopes are the same. Okay. M and M. Okay? Because they're asking, assuming the slope changes, let's see. No, is there a reduced model? Actually, it says the analyst estimate the parameter of such a model, assuming that the slope of the line changes, it actually equals 200. Do the data support the use of the model? Actually, there is no reduced model. Okay, there's a potential reduced model, but he didn't actually ask you for one. Okay, he didn't ask is the slope the same. That would be asking whether the slope is the same. It looks like that's what he asked at first, but no. That's not what he asked. He didn't ask any of that. He just asked whether this general model here, this general works. Okay? I studied the residuals, so the residuals have the good pattern. Okay? So there is no reduced model. Okay? I think maybe I'll skip this. So there is a reduced model in the exam problem, though. Everybody clear about that? Because that's what the condition that alpha 0 plus 10 alpha 1 equal to gamma 0 plus 10 gamma 1, where this was the line alpha 0 plus alpha 1x, and this is the line y equals gamma 0 plus gamma 1x. This is the condition that does not t. The not was at 10 here. T equals 10 in the exam. Okay, so this is the condition that the two functions match, all right, at this not, and therefore, since linear functions are continuous themselves, all right, the right limit and the left limits are equal, and so you have continuity under this condition. So this is if and only if H naught holds. Okay. So how do you model this thing then? How do you model the general linear spline? They show you in page 235 in chapter 7. The general model, page 235, chapter 7. Okay? And so it is. I think we did this last time when we talked about splines. We talked about beta 0, 0 plus beta 0, 1x, all right, plus beta 1, 0, x minus the not t, plus to the 0 power plus beta 1, 1, x minus t plus to the 1. Okay? That's a general linear function first, and then another linear function where you're changing the intercept. How does that work out? Because what does it work out? If x is less than t, check. If x is less than t, okay, then ey is equal to beta 0, 0 plus beta 0, 1x. And these are both 0. Okay? And if x is greater than or equal to t, then EY is another linear function. It's beta 0, 0 plus beta 0, 1 x plus beta 1, 0. That's just 1 if x is bigger than t, greater than or equal to t, plus beta 1, 1 x minus t. Okay, so the new slope is not beta 0. Well, yes, the new slope is beta 0, 1 x. Excuse me, beta 0, 1 equals, let's put it this way, beta 0, 0, there's a bunch of junk for it to intercept, okay? But in order to get a general intercept, well, I'll discuss that in a second. So this not t is fixed. Plus beta 0, 1 plus beta 1, 1 x. Okay, so that's the slope of the new, that's the new slope. Okay, the slope of the second one, the gamma 1, so to speak. This is my gamma 1, and this is my alpha 1. Now, to make alpha 1 general, okay, I need to make gamma 1 general, so I need to just change beta 0, 1 by a free parameter. That's beta 1, 1 in this picture. You see? But now beta 1, 1 is fixed, basically subject to what I wanted gamma to be. Gamma 1. And so then I need, so that's fixed, so I have beta 0, 0 minus beta 1t, that's some fixed thing, and now I need to be able to change that beta 0, 0 in general, so I have to be able to add another parameter here. Okay, because this beta 1, 1t is actually constrained. In fact, the t was given and the beta 1, 1 is fixed so that I get my gamma 1. So I really did need this many parameters, even though it looks like there's too many parameters. Okay? Okay. I'm sorry, this was my gamma 0. I keep messing up my notation. Gammas, I had my gammas, so it was the intercept. All right, so that's how it works out, and that's what he's trying to explain in the book. It's maybe not that easy to explain. Okay? Here's my alpha 0 and my alpha 1. Okay? So that's what you do, and how do, therefore, you just put in these, for the general model, you just put in the column of 1s, the column of x, the column of x minus t, plus, which we saw was 0s and then 1s. And then you put in the column of 0s and then x's, except that it's x minus t's. Okay? So that it comes down to, well, does everybody know how, I think you can fill in those columns at this point. You were here last time, right, when I did that? Yeah. Okay. I have an example on the page, so you can look at it if you need to. Double check how that works. So that's the easiest way. Now, what's the reduced model? By this method, the reduced model is continuity is just the beta 1, 0 is equal to 0. So you take out the third column out of the 4 columns. So the X matrix was a full model. X matrix is 1, 1, 1, 1, 1. Okay. X1, X2 down to Xn. 0, 0, and so on, 0, and then 1s. Okay. And then 0, 0, and so on, zeros, and then xn1 plus 1, whatever, xn2, 1 plus n2, or whatever. So how we worked with it last time. We wanted some notation somehow to indicate the breaking point. So actually, this is but minus t in this case. Minus t. So the x's were naturally ordered in this case, where the x's are sorted in this example. Okay? The x's are sorted. And this was x less than or equal to t. These rows correspond to x less than or equal to t. X less than t here and x greater than or equal to t here. Okay, and if x is equal to t, then you simply get zero there. Okay? That was a full model, and then the reduced model for your exam problem was to take this column out. All right. So the test of the hypothesis, which was kind of nasty if you set it up a different way, is just h naught beta 1 0 equal to 0. Okay. Simple T statistic will handle it. Okay. Anyhow, that was. Hopefully you thoroughly understand this problem now. And your homework problem for tomorrow. Anyway, it will be a rehash. Easy one. Okay. So, and I guess, anyway, we'll have some kind of little test tomorrow. Okay. I think the way I set that thing up was, I just took some of the Anova tables off the actual solution. Okay, and ask you some things. Okay, maybe slight variations to the problems, maybe not exactly the same problems, but okay. Took basic data and say, can you just regurgitate what you just did? Okay, if you got it wrong, then these are supposed to be the right answers. Okay, in terms of the numbers, so your numbers might not match exactly. Don't worry about that. Okay, the main thing is if you did it the right way. Okay. If there was an error in the data, I noticed that one person brought it up, you did last time, that the FTP site had the data wrong on the jojoba oil problem. They had one of the x's was 1. X1 was 1 on the second observation. It was supposed to be X1 was -1. That changed your estimate of SSPE drastically.
What if she didn't catch that?
Then you didn't catch it, and I'll just grade it as you have it there. I mean, there's two possible solutions: one with the wrong data, and one with the right data. But but the problem is that I told you that it did have a lack of fit. Okay, with the right data.
Yeah.
Okay. So you should be able to check your data. I didn't catch the fact that there was an error on the website until later. Yeah, that's a nasty thing. Okay. Sorry about that. The data was so easy to plug in, I just did it by hand. Sometimes you get a familiarity with the data by plugging it in by hand. Okay? Just sort of you have to look at it and so on. So I'm taking the back of the book as the correct data. But I'll take the FTP side also as the correct data for this example. I have to grade it both ways now because I didn't notice that until it was too late.
So it'd be 14?
Yeah.
Okay.
Actually, no, it was B14.
No, it's from...
It was a problem 418. Problem 418. That was a different problem. 418.
Yeah. X sub 1 has a negative 1 in the website.
Oh, X sub 1 has a negative 1. Oh, X sub 1 has a negative 1. That's what it is. Yeah.
Which gives you then 2.
It gives you an extra point where you can actually calculate pure error, even though it wasn't supposed to be, because this was a central composite design and there wasn't supposed to be that. So if you read the problem and knew what a central composite design was, you'd see there was a mistake in the website. In the FTP file. Anyway, each of the X combinations was supposed to be repeated just once around the circle, and then you're supposed to have repeats at the center of the circle for the central composite design. Oh, well. There were never ways to check what the right answer was for that problem, but I'm sorry.
I got a question about the other ones of that problem.
Yeah.
But I wonder if I just missed something in the notes, but the way that I saw to do a lack of fit testing for a multiple linear regression was really ugly with the DIIs.
That was a general one where you didn't have exact repeated measures.
So I looked wrong.
We didn't have exact repeated measures. Here you have exact repeated measures. At the 0 point of the central composite design, you have repeated measures, right?
I'm not talking about the same problem, though.
A different problem.
Yeah, the first. Was it the first problem that we did?
Oh, you did a lack of fit analysis for the first problem?
Didn't you say to do
Which problem?
Number 1.
No, I don't think so.
Just those numbers.
No, I didn't ask for any lack of fit on problem number 1 without property evaluation data.
What do you say compare the fits, I guess?
Okay. Okay. All right, well, if you did that, boy, that's extra credit.
Well, I didn't do that.
Okay. Oh, no, you didn't. You didn't need to. No.
Okay. I gave up on that.
Okay. Yes, there is a general procedure to sort of copy and make sort of have an automatic version of strata. Okay. Stratify the data, and I didn't cover that. I didn't expect you to do anything with that. All right. Yeah, that's the problem with the take-home exam. You don't know how much you're supposed to compute either. Well, I'll try to make it clearer. Let's go on. Let's go back to one-way analysis of variance, which we really rushed through at the end of the last hour. And I think I'll follow Shane's cue and say, well, you need to cover that again anyway, even though I wanted to get through it. Let's have a look at it just a little bit more before we pass on to the next stuff. Are there any more questions about the exam or the homework that's due? Other comments? No? Anything? Okay.
So on 6.2, how you showed us the betas and the
yes.
But did we do co-ratios? Did we want that?
No.
Part of
No, I don't want that. Okay. I want only whatever I show you. DI, which had a formula of something like RI squared over I forgot what it is, HI over 1 minus HI. Oh, there was a P here or something like that. You had to calculate Cook's D, and you had to calculate the DF betas J. Okay.
So all 9 regressors.
Yeah, but it should just be a pretty easy computation, isn't it?
Well, I was just.
You have to calculate. What you really need to do is you need to calculate. Yeah, but the columns come out. You just have to pull them across. You need to calculate that R matrix. Is what you need to do. Okay. You need to calculate this R matrix. R matrix. I can't turn the computer on because it won't go on today. So, how do you calculate these DF betas? The HIs, by the way, it was pointed out another way. Instead of taking this column from the diagonal of the H matrix, you can also do it the fact that HII is equal to XI prime X prime X inverse XI, where XI prime equal the ith row of X. So you can do it automatically this way too if you want it. If you'd rather use that than the. So how would I do that? I still have to use some matrix multiplication, but it could be a pull-down formula as long as I referenced this X prime X inverse. Okay. So I'd have to, it can be done this way as well. That was just pointed out. Okay, so with matrix multiplication, I think the way I showed you taking the column of the diagonal of the capital H out is a little bit more straightforward, and it's easy to do at this point.
That X prime on it is the ith row, or?
Yeah, XI prime. That's the way the author did it. Okay, in other words, this XI prime is a row vector. It's 1 XI1 XI2 over to XIK. XI prime. This is the way.
That earlier in the class, right?
Yeah, I mentioned the fact that even though the ith row is just this, and so why do you put a prime on it? Okay, it would be natural just to call it XI, all right, with a vector sign over it. But because a vector is generically a column vector, he wrote it as XI prime, just for that reason. Okay. Yeah. Otherwise, it doesn't make any sense. Notation, but that was the way he did it. Okay. All right. So you can do it that way. So in other words, you have this just sitting there as a row, in fact. All right. Because you have your regressor, you have your 1, you have your, let's say, x1, you have your x2. This is the property valuation data, for example. Okay, and this was taxes, right? This was the number of baths. This was the lot size, etc. Okay. You have 1, 1, 1, 1, 1, and then you had your, I forgot what those numbers are. But you had basically x11, x12, x1, 3, and so on. Okay. And then up to x1, 9 for the 9th regressor. Okay. Which was, I forgot, x9 was whether you had a garage or not, or fireplace, I can't remember. Anyway, this row right here, okay, you can put that in a formula, right? In a matrix multiplication formula, right? What would you do? Let's see if I can figure out how you would do it. You would highlight this row. Okay, so up in the formula bar, if I wanted h11, how would I do that? I'd highlight that cell, okay, which wouldn't really matter. Then I'd up in the formula bar or in that cell, I would say equals m mult. If you want to use this method, right? You'd have to have x prime x inverse already referenced. All right, let's call it C or something like that. So you have, and then you have x prime x inverse that's already referenced. And it's a 10 by 10, which is the problem with the capital H matrix is that it's big n by n. So if you really had a lot of data, it'd be a pain, right, to actually write, make a big space for H and reference and so on. You'd have to be counting columns, to make sure you get exactly the right number of columns or at least enough. Okay? So your reference x prime x, let's just call the reference C. All right? And then you would put m mult, then you would highlight this row, whatever you want to call it. Okay? If this was row A and this was column A and this was row 2. Okay? In Excel, then you would do what? A2, I guess that's times, I think this is how it works. A2 to, whatever the 10th one is, A, B, C, D, E, F, G, H, I, J, J2, all right? And then times C, and then you do another matrix multiplication. I can't really check this because the computer is not working. And then you would do, I'd have to take the transpose of A2 to J2. And then you want C to be fixed, so that's why you want a reference, because you always want it to be the same. Okay? And then you have to shift control enter. And then you should get HI, and then you should just be able to pull this down. The A's and the J's should be as they were before, and the 2's will ratchet up. So you should be able to get your HI column that way as well. Do I have enough commas in there? Okay. Parentheses, yeah, that looks okay. All right, so that was, do you understand what I'm doing there? It's just this formula. I'm saying, here's how you would calculate this formula. This formula for each, and then when I pull down this form, then I'll pull it down. Okay? I'll pull it down. These will go to 3 and 3. The C will be referenced. It's fixed. Right? It's this fixed place, so it doesn't move. As long as you first have to calculate x prime x and then x prime x inverse by putting in the 10 by 10 array and doing those formulas first. Right? So there's still a fair amount of calculation, but you don't have to write out the H matrix completely if you don't want to, and then that ugly formula for pulling the column of H. But by now I've memorized the formula, so I know how many parentheses and everything. Okay? So that makes it even easier. Okay?
It's definitely worth it to keep your matrix name as M.
Yes.
Oh,
you like M? Okay. Oh, okay. All right.
So the x around is another row?
This is a row. This is a column.
It's a column.
Yeah, because it's the transpose of this one. You need, because how does this work out? Why is that so? Because you have H is equal to, let's demystify this, x prime x inverse, x prime, right? So what if you look about that? That's just going to be the x matrix. 1, 1, 1, 1. I just did this. X1, 1, Xn1, X1, 2, down to Xn2, etc. All the way down to the 10th column. right? This is a n by 10 matrix, okay? Then you have this little 10 by 10 in here, which is the C matrix, the x prime x inverse, okay? And then you have x prime again, which is a 10 by, which is a long and wide matrix, okay? This is a 10 by n. Okay, and then this has the 1, x, 1, 1, x, 2, 1, and so to x, n, 1 over here. Okay? And then 1, x, k, 1, excuse me, x, 1, k, x, 2k, over to x, n, k over here. Kth regressive. All right. So what is the II entry of this product matrix? You take the ith row on the left and take the ith column on the right. That's how you get the II entry of any product. All right. So the ith row on the left and the ith column on the right. All right. That's the ij entry. Okay. So then you're just. So then here's the second version. Okay, so I didn't transpose it correctly. I should have had ones over this. 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay. Yeah, I got the ones in the wrong place. No wonder I can't figure out what was going on. So I want this column here. That's what I was talking about. So then it was x1, 1, x2, 1 over to xn1 here. Okay. x1k, x2k over to xnk. Yeah, I got my ones in the wrong place. Okay, that's what the transpose looks like. Okay. So now it looks correct. I'm taking this row, okay, in this column for h22. All right? All right. So this is the alternative method. Everybody following? All right. So you go ahead and you have to calculate your SI squared and all that stuff. So this is the only difficult part of the computation, really. Everything else is just pretty straightforward, except for that R matrix. Because what did I have for this? DF beta is, what was it, JI or something like that? What is that business? Okay, for each beta 1 through 9, you're gonna have beta DF. You're gonna have DF for betas. Let's see. I've got the way I notated it on this one example. Where was the example? Just had it out here a second ago. Here it is. It was the wine data, okay? And so then I had DF beta of J. I had J equals to 0, J equals to 1 for the intercept, J equals 1, J equals 2, and so on. You'll have to do up to J equals to 9, right? All right. And so how do you actually calculate that? The definition of DF beta of JI, what is it? Let's see if I can remember. Is how much the standard error of, so how many standard errors the beta changes by, right? So it's beta J hat minus beta J hat when I take the ith observation out, divided by what is the, then I'm going to use the deleted estimate of variance, okay, SI squared, and then I have what is the variance of a beta J. There's a square root of CJJ down here, right? Okay, and we worked out a formula for that, okay, as to what this actually is. And the formula a certain matrix. Okay, R matrix. Let's see if I can remember the formula. I can't remember the formula. It's on page 214. Yeah. And I mentioned this, that this comes out to be little rji, which is a certain ji element of a certain matrix, divided by the square root of rj prime rj, which is the square length of the vector r. So there's a vector r. Okay? And rj is actually a good old column vector. Maybe I could just put this as inner product. It's easier to write it that way. Okay? Okay. As the formula goes. And then this is a ti. And the square root of 1 minus hia, where ti already was the r student. Okay, which is easy to calculate. Okay, what is rj? rj equals the jth column of the R matrix, which has n rows and p columns. Okay, where p in this case was 10 for your example. Okay, it's 10 for the problem 6-2. Okay, all right, and R is defined simply to be x times x prime x inverse, I believe. This is n by p, and this is p by p. Okay? And what you have is that r prime r is equal to, or r prime, I'm sorry, r prime is equal to what is it equal to? It's equal to x prime x inverse, and then you get is this correct? Looks like it was a mistake.
They show R with the theme x inverse x. Sorry, how did you say it right? The C matrix with the x.
Yeah, I don't have this right. Okay. Let's see, how did I define R over here? R is okay. No, times x prime. Let's see. I've got an R. Maybe I've got R prime written down then. Therefore, is this K R? Is the jth column of R prime then? Okay, this is apparent. R prime. Well, R prime is x times C. Okay. Yeah, I see. RP0. That's what I have. I'm sorry. Yeah, this is the jth column of R prime, n by p, where R prime is equal to x prime x inverse. Okay, and R prime. It's just a matter of where you put the primes to define this R matrix, and it's a little bit arbitrary, but this comes out to be then x prime x inverse times, okay, this thing, x prime times x times x prime x inverse, which comes out to be the C matrix, equals x prime x inverse, equals the C matrix. Okay, R prime. Okay, so that means R prime is a bunch of columns, so it's tall this way. Okay, this is R prime, and here's R. Okay, and I've got R1 is the first column of R prime. I've got R2 is the second column of R prime, and so on. P is the pth column of R prime. And RJI is the JI element of R. Okay, so RJI equals the JI element of capital R, which is this matrix. Okay, which means basically I'm looking at see, okay, that just is, so this is the jth row in the ith column of this matrix, okay, which corresponds to the ith row in the jth column of this matrix. So this would be ith row and jth column of this matrix of the R prime matrix. So the R prime matrix is more fundamental to me than the R matrix. Okay, and that's RJI then, is what that number is there. RJI equals RIJ prime. Okay, RJ equals RIJ for the primed matrix. Okay, there's not a good notation for it, but I'll just call it prime here because it's not a vector. Okay, or R prime is what it would be. R prime sub IJ. Okay, that's the IJ element of the R prime matrix. So this is RJI. Okay, that's RJI. All right, so what's happening is that if I take that vector and take its square length, that actually is equal to, if I take this vector R, which is what he's denoted here, this RJ, okay? So he's actually written it this way. That's the jth column of R prime. All right? So it really should be called, there should be a prime on it. But anyway, that's what he did. So he's kind of mixing his notations a little bit. If I take that vector there, okay, the jth column of R prime, which is simply obtained by taking the jth column of XC, okay, jth column of XC. So what I do is I take my X matrix, it's got the 10 columns, I multiply it on the right by C, and I get my R prime. And that's all I'm going to do here. I'm going to write R prime matrix is X times C. And I'm going to write that down. And that's going to be exactly what I want to plug off these RJIs, okay, at the ith row. All right? And that's where this is going to come from. Now, how am I going to get this CJJ? I can get the CJJ either from my reference or it's kind of magically as the square sum of the squares of the entries in this column. Okay, so if I take the sum of the squares of the of this column, all right, jth column, I'm going to get CJJ. Sum of the squares of the RJI. Okay, I goes from 1 to n, that's equal to CJJ. Okay? Because CJJ is the jth row here, jth column here. Alright? Jth row, jth column. That's what CJJ is. Jth row in the jth column gives me CJJ. RJ. Whatever. He didn't tell me whether RJ was supposed to be a row or a vector, but I assumed that it's supposed to be a column. So that means I'd have to write RJ prime times RJ. Okay. Where this is RJ. Okay? And this is RJ prime. Okay? Okay. So that's what this is, and all this other stuff is the wraps up into the other business. Okay. So that's how it's denoted, and I showed this on the example with the line data on the website. What's confusing about that is I have denoted the columns of R prime as this. If you actually read that, I wrote RP0, RP1, and so down to RP5. In the case of the line data, there were 5 regressors. Okay, so this P stands for prime. Okay. Okay, because RP was R sub P was equal to again XC. So this is in the website. for wine data if you want to look at it. So you can see exactly what I did. So once you get this R matrix in, which is a triviality, then what you can do is reference the TI somehow by freezing its location. You have to be a little bit careful with your indices. Okay, so you're going to reference the TI has a location, and you need to put the dollar signs in Excel. Okay, you need to put the dollar signs here and for the HII, but you don't want to put the dollar signs on here because you're just going to pull this whole array over. All right, to get the right formulas for the DF betas. I don't know if you understand that or not.
What was the shortcut that Shane used for the inserting the dollar sign or changing the dollar sign?
F4.
F4.
Yeah, it cycles F4, and it puts both dollar signs, then hit F4 again, and I don't know what it does exactly. It removes one of the dollar signs, and then it removes the other one or something. Okay? So you have to be careful which dollar signs you go in, because you want to reference you want to fix the column of TI, and you want to fix the column of HII, but you want the row to vary. Okay? Is everybody following that? So, and then I'm picking off this CJJ is the square root of the sum of the squares down here. Okay. So I have to put a square. I took the square root of this one down here. All right. Now you can see the formula in the wine data. You can just copy it almost verbatim. Okay. If you need some help with this. And to check your computations, I don't know. That's people wanted to check it. And if I could have my house data up here, I'd show you, but I can't show you right now because the machine is down. Okay.
I don't know if the house data has any joint influential. We don't have to worry about that either.
Joint influential points?
Yeah.
What do you mean? I don't think I didn't talk about it.
No.
No, I didn't talk about.
Avoid that one.
Yes.
Just do our basic ones.
Yes. What you have is that you do have some multicollinearity in the data, but you can avoid talking about that too. All right. I just want you to be able to just do this dang calculation. That's pretty much what it is. I'm forcing you to go through the calculation once. Okay? Sort of go through the formulas once, so if you ever saw it again, you'd be able to do it, perhaps with a little bit more effort. A little bit less effort the second time around. Okay? Anything else about that homework problem? Okay. A DF fits was also another column you had to put in, but that was fairly straightforward as well. It didn't require this R matrix at all. So you have to calculate. I think everybody's been doing it. They've been calculating the SI squared. They've been calculating the HII. They've been calculating the RI and the TI pretty routinely. DI squared is DI, Cook's D is therefore a triviality by comparison to these DF betas. DF fits is also fairly simple. So it should take you 15 minutes. Okay, if you're lucky. Don't mess up. Okay. All right, let's go on. Let's go back to the one-way analysis of variance. Hey, how you doing? You made it.
Yeah.
Was it hard?
I had to drive myself.
Uh-oh. That again. Your driver's on the blink, huh? Okay, one-way analysis of variance. The cotton data, let's look at that one more time. Okay, so I had cotton percent one-way analysis of variance. I had the cotton percent the levels were 15, 20, 25, 30, and 35. And I listed the data of problem 811 in columns rather than in rows, just because that's the way I wanted to organize it. So the data was this. It's fairly simple to write down everything. There were 25 data points. These are the strengths of the fiber. I don't know what the exact units these were in. Okay. So these were the strengths. So this was cotton percent. That's the qualitative or categorical regressor. Okay. It's a qualitative regressor in essence. And then I have strength. But actually, the way we set it up with a regression model, how many regressors are there? How many regressors are there when we actually set it up? In the regression model, there are 5. Including the column of 1. There's 4 regressors and an intercept. So what we're doing is that we're allowing for a different. What we're really doing is allowing for a general function of the cotton x. All right, if x. In other words, if I wanted to have a general function on 5 points, how many parameters would I need to represent such a function? In other words, just any. If I had a function f and I had 5 points a, b, c, d, e on the x-axis, and this could even not be an x-axis, just 5 points, okay, in the world, okay, and I wanted a general function and a numerical function in this case. So this is a real axis here, okay. All right. To denote the function. How many parameters would I need? Okay. For a general function, no, I need 1 parameter for each height. Okay. I need 5 free numbers. Okay. So if I call this, I'm going to call them U1, U2, U3, U4, and mu5 would be the 5 general heights. Okay, I just need. In other words, I need the most general function. There's no restrictions at all on the heights. Okay, so I need 5 free numbers: mu1, mu2, mu3, mu4, and mu5. That's what I'm saying here. So instead of having, a linear function, I need 2 parameters, right? A quadratic function, I need 3 parameters. Cubic 4 parameters. Quartic 5 parameters. So it would be, in some sense, it would be equivalent to fitting a quartic polynomial, all right, to this data, where x was the cotton level, 15, 20. 25, 30, or 35. I could just as easily, and I'll get exactly the same fit. Okay? Of course, I would be able to predict with the quartic model, and I won't be able to do any prediction at all with the model that I'm going to come up with. Okay? So you may say, well, why not put the quartic model in? Fine. Okay. In general, you wouldn't be able to because you won't have, numerical values. But you could. You could just sub any numerical values you want. Okay, so 5 distinct values if it was a categorical variable, and then fit a quartic model. All right, and you would still. Okay, it just would be meaningless. Okay, because it may not predict well at all. You may say, well, if it was definitely categorical categories, then what's the quartic going to do? Okay, if I had 1, 2, 3, 4, 5. As my codes for the 5 categories, A, B, C, D, E, okay, that fit the quartic. what does it mean to fit it? What does it mean to predict the mean at at x equals 6 or something? It doesn't mean anything. Okay, well maybe I should show you how to do that. But we should just play with the Fortic model and just do it anyway. All right, if you can do that. Maybe I can do that when we take the break. I'll just come and give you the results. Okay, from the Anova. Okay, make sure it's the same. What I'm going to do is show you the classical Anova, and that was that the classical version is to allow a different mean for each of these columns, right? Classical model, Anova model, is simply just say that mu I is that E, well, I call these numbers Y. He switches his use of the I. Y1J. J goes from 1 to 5. He calls these Y2J. J goes from 1 to 5. And up to Y5J. J goes from 1 to 5. Now it just turns out there were 5 observations in each column here. All right? And also 5 categories. All right? Had a categorical variable. Okay, with 5 possibilities. So, I think that there are 5. K equals 5. Was in the notation of the book is the number of different levels of my categorical variable. Which matches kind of, therefore, the number of regressors I'm going to talk about in my regression model. Okay? K instead of P. But remember, P was equal to K plus 1 before. Now K is K. K is equal to P. Okay? So it's just that's why he kept that notation, I think, with the K. It is very close to the meaning is very close to what it had before. Classical model is that mu sub I is equal to a grand mean mu plus tau I, a differential, away from the grand mean. I goes from 1 to K. All right? Which is, and then EY IJ is equal to, I is now different than the observation index. It's the regressor index. He switched it, the I and the J. That you could complain about. Okay. But he switched it here in the end of chapter 8. Let me just point that out. It's hard making notation consistent throughout a whole book. Okay. And what he did was he has the J going from 1 to N. Okay, which corresponds, is a flippage anyway. So he's got I goes from 1 to K. That was the number of different categories. I treatment or factor level. Okay, he's got the I treatment or factor level. I equals treatment index. Probably because it's from the classical version of analysis of variance. If you see it in other books, that's the way they do it. Okay. So unifying the two subjects was not an easy task because he had to switch his I and the J. Okay. So then therefore this is mu plus tau I plus epsilon ij. Okay. J goes from 1. J goes from 1. He calls up to N. In general, you can do N sub I. All right. You do not have to have the same number of observations in each column. In fact, the graduate students have to deal with that. Okay. And problem 8.9 for next week. Okay. Just set this up. See what the X matrix looks like, and so on and so forth. Okay. And in here, if N sub I is constant, he calls N. So that's the number of observations that you're going to make under each treatment level. So we call these treatments. I'm going to put cotton 20% into this fabric. That's the treatment. Okay? Or in, treatment, sometimes you consider that from the medical sciences. That's more of a medical sciences term. Right? I'm going to treat this patient with 2 aspirin. I'm going to treat that patient with 2 Tylenol. I'm going to treat this other patient with, nothing, a placebo, and so on. And then of course you have a group of patients that have those different treatments. Okay, and see how their temperature responds after, some exertion or something like that. I don't know. I mean, you come up with some medical experiment. Okay. So, or make them jog or something. Okay, or make them have a migraine. I don't know. But anyway, you have to have some kind of situation. All right, does everybody follow what's going on then? Treatments, or they could actually be. And I think in another example, the treatments they're just different things like lab 1, lab 2, lab 3. Lab 1 makes aspirin. I'll just move my metaphors around a little bit. Lab 1 makes aspirin and has a certain percentage of active ingredient. You'll actually assay the aspirin and see how much active ingredient it has. Okay, and you'll do that maybe 5 times. All right, or maybe 10 times. Okay, from lab 1. Then you do the same thing for lab 2. You're making the same aspirin supposedly, but it's a different laboratory setup. Blah blah blah. So the active ingredient actually comes out a little bit different, maybe. Okay, so you have lab 2, and then you look at the percentage of active ingredient or something in exactly 5 milligrams of aspirin or something of a tablet. When it's supposed to be 5 milligrams of the active ingredient actually, but what is it exactly? And then so on for lab 3. So are the labs the same? Do they all have the same effect? That would be all the tau i's are equal to 0. In other words, the mu's are all exactly the same. Okay? So, and of course, here all the mu's exactly the same. We just mean that all these fabrics have exactly the same strength. You don't expect that, okay, in this example. All right? Because they're really different percentages of cotton, okay? Whereas in the lab's example, they were really trying to make the same thing, okay? But maybe in terms of strength of fiber, cotton isn't that big of a deal. I don't know, So that was the question. So then the basic hypothesis is that tau I equal to 0 for all I, which means that all treatment levels are the same. I mean, the treatment level has no effect on the mean. All right. Treatment has no effect. Okay. However, here there were 6. If k was equal to 5, as it were in this case, k was the number of levels of the treatment. Then I had actually 6 parameters. Count them. You have 1 mu and 5 taus. So that's too many parameters. It was redundance. Okay. So therefore, there was one condition with summation of the tau I equal to 0. One linear condition on the taus. Okay. So how would the taus be? If you gave me five numbers, how would you define the taus? Just give me 5 numbers. Not too easy, but not too hard, too. All right, give me 5 numbers. All right? 5, 6, 7, 8, 9. That was too easy, but anyway. There. Okay, so what are the... so what's the... If these are the mu1, if this is mu1, mu2, mu3, mu4, and mu5, then what's mu and what's tau? Then mu is 7, and tau 1 is -2, tau 2 is -1, tau 3 is 0, tau 4 is 1, and tau 5 is 2. Okay, so I just take the average of the numbers. Okay. Mu I. So mu is really the average of the mu i's in some sense. If I just had 5 numbers like that. Okay. So you can think of it that way. That's how I represent 5, 6, 7, 8, 9 by mu plus tau I. Okay? The sum of the taus is 0. I just take the average. All I did is take the average of these numbers. Okay? And then take the differences from them. Then automatically those differentials sum up to 0. There's not a whole lot of need to discuss this further, I think. Okay, there's an if and only if. It's just a way of representing the 5 numbers as a grand mean plus differentials from the grand mean. That's the classical parameterization we mentioned. Classical Anova model parameterization. But it's not the only way you can parameterize an Anova model. There's lots of ways of doing it. I said we could do it with in the case of 5 categories, you could do quartic regression on some coded variables. You wouldn't even have to code the variables very much. Just the variable x would be 15, 20, 25, 30, and 35. Okay. So there's now more than one way to do it, and what the author suggested is this. The way he did it was introduce the indicator variables. And so the author's approach is to say that mu1 he writes as another parameterization. Is mu1 is beta 0 plus beta 1. An intercept plus a beta 1. Mu2 is a beta 0 plus a beta 2. Mu3 is a beta 0 plus a beta 3. Mu4 is a beta 0 plus a beta 4. And Mu5 is a beta 0. Okay? So I'm going to go beta 0 through beta 4. Have 1 intercept and 4 regressors. I like intercepts because it's so common, right? Automatically assumed in most multiple regression models. And so I'll go ahead and keep an intercept here. The only somewhat bizarre is that he kept the intercept as the last. he called the last mu5 equal to the intercept. Okay. In other words, it might have made a little bit more sense to shift this whole thing down. Mu1 is beta 0, Mu2 is beta 0 plus beta 1, Mu3 is beta 0 plus beta 2, Mu4 is beta 0 plus beta 3, Mu5 is beta 0 plus beta 4. That would seem more natural to me. Okay, it would have fit exactly the way he brought the indicator variables in the first half of this chapter as well. Because now the indicator variables have to be shifted up. Okay. He was going for that. Oh, I got you. All right. He could have gone mu0 through mu k minus 1 too, but oh well. That wouldn't have been too classical either. So yeah, you can see there's different ways of doing it. There's not only one way to set this up. Many ways to do it. Juggle them in the middle. Okay? So now, yeah, so I think see what you're saying, Joe. Yeah, these parameters match, so that's what he was after. So how would I set this up, therefore, as what would the regressors be in order to set up this? I want now xb to be equal to this thing, right? This equals x beta, okay? Or b0 through b4. All right, so it's easy to figure out what x would be, is it not? In fact, I could plus 0, b5, b plus 0 here if you want. So how would I get that, you see? You can see the x's. I'm sorry. This is x. This is model for means. I have to be a little bit careful because this is going to be repeated. Mu1. I need mu1, mu1, mu1 for the first 5. Right? Then I need mu2, mu2, mu2. This is the model for means actually like that. right? Because if I think of the y vector, e of y, if I put these 5 numbers first, then these 5 numbers, that's the way I'm going to do it. I'm going to put my y as this column, and then followed by this column, then followed by this column, then followed by this column, and then followed by this column. So let me put the y in. Y is going to be 7, 7, 15, 11, 9, and then 12, 17, 12, 18, 18, etc. Okay? I'm going to put it in blocks like that. Okay? And then that will correspond, therefore, to e of y, the model for means, equal to mu1 in the first 5 places, right? Because the mean of each of these entries, these are random entries, the 7 is random, it's 7 plus epsilon, right? I mean, the 7 was the y plus epsilon, okay? But EY is therefore mu1 in that first place. The expectation of the 5th position is mu1. The expectation of the 6th position is mu2, down to the 10th position, mu2, and so on. So this is the actual model for means. So what I'm thinking, why I was checking myself as to whether I made a mistake here in what I was writing down, okay, was that I needed a full n vector. Okay, this has to be n by 1 for my model for means. That's what x beta is. This is an n by k, and this is a k by 1. Okay, I need an n by 1 column, all right, for my model for means. All right, this is my model for means. In a regression case, there's x's in there, and it's beta 0 plus beta 1x. Okay? So on. So, and then the x is in there. But so it keeps changing all the way down. Here it's constant for pieces. Okay? And so that means this is beta 0 plus beta 1 repeated 5 times. And so on, then beta 0 plus beta 2 repeated 5 times. So it's in blocks. Okay. So there's actually 25 equation signs here. All right? So then, now that I've got all those equations written in, I should be able to peel my x matrix off, right? X is just 1s for all these betas. It's 1s where there's a beta 1 and then it's 0. Okay. It's 1s where there's a beta 2, which is the second block. Okay, and then it's 0. And 0 and then 1s and then 0. It's 0s. You have all these betas 3s in here. Plus this. Okay, a bunch of times. Okay, and then 0's beta 3s and then 0's. Put in the beta 0 plus beta 4. I guess I didn't do exactly like this last time, so maybe this is better. And then beta 0 plus 0, there's zeros. There's nothing more. There's nothing but zeros in here now. 0. Okay, plus 0. Okay? Now it's beta 0 plus 0. Okay? So break it up like this. And break it into columns like this. And then you can just see your x matrix sitting there. X is equal to 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and then 0, 0, 0, 0, 0, all the way down. I need to make 5 levels here. 1, 2, 3, 4, 5. Okay, 1. 0's all down in here, and then it's 0's, 1's, 0's, 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 0, 0, 0, 0, 1, 1, 0, 0, 0, 0. I'm not putting all 25 in the columns, obviously. And then the fifth one, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, and then 0, 0, 0. Okay, like I did last time. Okay, n by 5, or 25 by 5 in this case. Okay? So then you have 4 in, did I make a mistake? Oh, this was supposed to be zeros in here. Okay. Those dots were zeros. So I got to distinguish between dots and ones. Okay, here's the ones. All right? All right. Okay, so you have 4 indicator variables. x1, x2, x3, and x4. Well, I'll put x1, well, it doesn't matter. This is correct. x1, x2, x3, and x4. So 4 indicator variables you have to introduce. quite simple. And then you just do the multiple linear regression on those 4 indicator variables with intercept. With intercept. All right? So there's only 4 regressors. K-1 regressors. K-1 indicator variables as regressors. And of course, they are mutually orthogonal. Those indicator variables are mutually orthogonal, but they're not orthogonal with the first column. It's actually quite easy to find the inverse of x prime x because it's mostly diagonal. What you have is you have x prime x is looks like n1, right? N2 down to nk. Those are the number of observations for each treatment level. N2 over to nk, and you have N2 to N1. I'm sorry, this is N over there. N1. How did they wait a second? Oh yeah, it's N1 up to nk minus 1 because it's right. It's N and 1 because it's this column into itself. How do you find x prime x? I'm going to teach you now the way I think about this. Okay, if I just got an X matrix sitting there, usually when it's full of numbers, I don't think about it too much. But when it's this type of pattern, I think about it easier. That is, to get the 1-1 entry is this column into itself. And to get the ij entry is the ith column into the jth column. So it's just inner products of the columns. And this column into itself, so if I want to get the first row or first column, it's a symmetric matrix. Take this column into itself, this column into this column into that, this column into that, this first column into the last column. Well, okay, so that's the column into itself is n. The column into the second column is n1, the number of treatments, the number of observations at treatment level 1. Okay, up to nk minus 1. So there's not, the minus 1 is down on the bottom of this index. Okay, it's not on the level of the n. Okay, in this case that's just 25, 5, 5, 5, 5. All right, and then I have, this is now n1, and this is down to n sub k minus 1. Okay, on the diagonal, and these are zeros off here. Okay, so it's got these it's not a diagonal matrix, but this block, most of it is a diagonal matrix. Okay, and there are ways to invert such things, little formulas for that type of a situation that you can do. There's a formula in the back of the book to how to invert that matrix. There's simple little formulas. Corresponding to easy solutions to the normal equations. What is the solution to the normal equations in this problem? What do you think? How would I minimize? I can go back to the original model. Summation yij minus mu I squared. Okay, j goes from 1 to n sub I, and then I goes from 1 to k. All right, this is the least squares problem, least squares estimates. How would I actually do that? The sum of squares, because that's what it is. If I'm just going to go back to the model for means, where I've just got mu1, 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 mu1. All right. I'm subtracting mu1 from this number, I'm subtracting mu1 from this number, I'm subtracting mu1 from this, mu1 from this, and mu1 from this, and taking the sum of the squares. That's what I've done here. Then I did subtracting mu2, 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 and the next one. And so that's my summation on I. Okay? How would you find the mu's for that? That looks pretty simple, right? d by d mu I, okay. d by d mu I equal to 0. And what does that give? So I'm not going to go ahead and invert that matrix. Actually, this is a way to invert that matrix, okay, in essence. How would I get this? Well, most of the terms would drop off, right? Because you have 5 terms with mu1 in it, then you have 5 terms with mu2 in it, 5 terms with mu3 in it, 5 terms with mu4 in it, and 5 terms with mu5 in it. So since all the so most of this outer sum goes out, all right? And it's just the inner sum that fixes here. And so I get then that 2 times yij minus mu I to the 1 times a minus 1 summation j goes from 1 to ni equal to 0. So that gives me, I cancel the 2 and the minus 1 if I like, and I just simply get yij, the sum on the yij, which sometimes on j, sometimes they use a dot notation. This means sum on the j, yi dot equals ni mu I, okay, because and then I get mu I hat equals yi dot divided by ni equals yi dot bar. Okay, when you divide by the number of summands in the dot, you put the bar over it. That's the notation, okay, if you ever get into this subject, analysis of variance. This is a dot notation. Sum on the j. All right. That's the definition. Okay. Well, anyway, it's just a simple thing. You just take the group mean. That's just the group mean of the ith group, or ith treatment mean. That's all it is. That's what mu I hat is. What do you expect? So this actually, and the numbers came out. They didn't come out real good in your notes because on the very bottom of the page. So I'm writing them down here. You could copy them by hand if you've got notes number 9. They were 9.8, 15.4, 17.6, 21.6, and 10.8. I believe those were the numbers that you got there. That's mu1. This is mu I hat. I goes from 1 to 5. This is I equals 1, I equals 2, I equals 3, I equals 4 group, and I equals the 5th group is there. Okay? And those are the mu I hats. Okay. So what you should have, and this is just abstract nonsense, is that beta 0 hat is simply the 10.8. It's just a mu 5 hat. And then to get beta 1 hat is simply going to be mu 1 hat minus mu 5 hat. Okay? Just subtract the things. Okay. So I'm not going to go through that. It's intuitively obvious that that's the way it's going to work out. So what would the reduced model be, though? That's a little bit less obvious intuitively. So what I get out of this is that, okay, here's the reduced model. It's H naught, right? Just one grand mean. Let me just summarize here, and then we'll take the break. If I have beta 1, so beta 1 hat's going to be mu, according to this model, it's going to be beta 1 plus beta 0 minus beta 0, the thing hatted, so that's going to be mu 1 hat minus mu 5 hat. Okay, beta 2 hat is simply going to be mu 2 hat minus mu 5 hat. And beta 4 hat, and beta 0 hat is simply going to be mu 5 hat. And beta 4 hat is going to be mu 4 hat minus mu 5 hat. Okay? And you can check this out because actually there is an Anova routine in Excel, which I would show you if the computer was working well today. But and so all the stuff matches up. I did it with the regression model. Okay, did the one-way analysis of variance with the regression model. Also did it with the Anova package. There's a single factor or one-way Anova. Okay, there's also a two-way Anova that's in the exercises of this chapter, which I can go through. But I think I'll probably wait till Monday to do so. Okay. I want to talk about maybe a little bit more about higher way Anova, and I want to talk about Chapter 13, and I want to get through Chapter 9 in the second half of today and whatever tomorrow I need for that, okay? And also that distribution theory stuff. I'm still holding on to that as a possibility. And I think we'll have some extra time next week, because after Chapter 13 is... Then we go back to simple linear regression or something. I think it's... Okay. No, there's some other stuff in there. There's a multicollinearity chapter, which is kind of interesting. But it's very computational. Okay. So you just work this out. So what does this come out to be? If you actually do the regression model, then U5 hat, this was the 10.8. U1 hat minus U5 hat, I believe that comes out to be the -1. So the actual, the x1 coefficient, the x1 slope comes out to be -1, right? And you'll see this happening, okay, etc.
Is that the reduced model? Is that what you said?
No, the reduced model. I haven't done the reduced model, so let's go ahead and do that. What is the reduced model? The reduced model is there's no treatment effect. How do you... What's the least square estimate of the betas then? What are the betas? The reduced model, H0, is equivalent to H0 beta 1 equals beta 2 equals beta 3 equals beta 4 equal to 0. So there's actually only 4 degrees of freedom in this hypothesis. This is what I pointed out last time. Even though this is 5 equal signs, 5 taus equal to 0, there's one linear condition on the taus, right? So they're actually not 5 free parameters. There's only 4 free parameters there. Namely the beta 1, beta 2, beta 3, and beta 4 in this version. These are independent parameters. Okay? So there's 4 degrees of freedom for the SSH. So what is SSH? You can get it from the regression model. It's just setting all the betas equal to 0 in a multiple regression model. So that's the number of degrees of freedom of the regression sum of squares. So if I actually look at the Anova table for the regression, I'll have regression, the sum of squares, and the degrees of freedom. Okay, this is SSR's degrees of freedom is k minus 1, because there are now k minus 1 regressors. And then the residual, of course, is SS res. And what does that have? That is n minus k. Because there's k. And then I have the total, SST. And that's n minus 1. The degrees of freedom add up. Okay. If I test this hypothesis, has exactly the k minus 1 degrees of freedom for the SSH. So SSH for this hypothesis, SSH equals SSR. Okay. With k minus 1 degrees of freedom. So all you're doing is you're testing whether the fit of the model is significant. Okay, so it's just the F test for the whole model. So it's trivial. I don't have to do any extra calculation. FH equals F for model significance. Because the null hypothesis is there's only an intercept. All right? Intercept only model. Okay. For testing model significance. So I don't have to do any extra work. Just code those. So one-way analysis of variance is really quite simple. Now to do it by hand, then you have to do some by hand calculations. You go ahead and you calculate each of these means. You plug it in here. You find these are so-called. This is a within group sum of squares. Okay, and then there's something called the between group sum of squares. Okay. Because this is going to give you SS res, the between group sum of squares is going to be the SSR. So the way they talk about it in analysis of variance is they call this the between group sum of squares. And why? There's a nice formula for it. In the balance case, it comes out quite simple, I believe. You have, okay, so what is it? SS res, then at least it comes out to be summation. Even in the unbalanced case, this is what SS res is. Summation j goes from 1 to n sub I, yij minus yi dot bar. Or maybe they just call it a yi bar there. Maybe they dropped the dot when they put the bar on. I can't remember. Anyway, put the dot anyway. And squared. Okay? That's what SS res is. And then you have SST, of course, is summation I goes from 1 to k, summation j goes from 1 to ni. What would SST be? It would be the error sum of squares where you're under the trivial model, intercept only. So what would that be? If I just had mu here, no mu sub I, differential with respect to mu set equal to 0, what do I get? I get the sum of all the y's is equal to mu. So this would just be the y, the double dot bar, I guess. Okay? You just sum over all the I and j, and then divide by the total number. This is yij minus that, okay? Squared. That's SST. Of course, it's exactly the same as SST always is. You just take the average of all the y's. That's y double dot bar in this notation. And you subtract from y and then take the sum of squares. Okay. So then the only question is, what does this actually come out to? Well, you can figure out what the SS res is then by subtracting these two formulas. You're getting the SS regression, SSR. This is the SS res. What is the SSR? You subtract these two formulas. Well, one way to do that is to expand each of these formulas by the shortcut method. And a sum of squares about a mean. We know what that formula is. This outer sum, I'll just go for the ride. And the inner sum would be summation j goes from 1 to ni, the yij squared, minus, the way it works is ni times yi dot bar squared. Okay? So like that. This is the only thing that's squared here. All right? Then this is outside, and that's on the k. All right? That's one way to rewrite that, because this is just the shortcut formula for expanding the sum of squared deviations. And then on this one, of course, I have the same shortcut. This is double sum yij squared minus the total n y double dot bar squared, where n is just the sum of uses all the entries. Okay. So now I can easily subtract, okay, these two things, because the sum of squareds things go off, and so SS res, one version of it is, let's see, it's this one minus that, so it's summation ni yi dot bar squared, I goes from 1 to k, minus n y double dot bar squared. Now in the balance case, you can actually write that down. So that would have been, so I could actually have calculated it here if I knew what the grand mean was. What is the grand mean in this problem? 15.04. Yeah, that was it. I wrote that down somewhere, or did you know that? Okay. Oh, you got the spreadsheet. So this came out to be, let's see if this comes out to be right, because I claimed that the SSR was, I can't read my writing at the bottom of this page either. What was the SSR? Oh, 475.76. Okay. So this comes out to be, in the balance case, this is going to amount to be 5 times, what, the 9.8 squared, plus the 15.4 squared, plus and so on, plus the 10.8 squared, okay, minus 25 times y double dot bar, which is 15.04 squared. Okay, and this supposedly comes out to be equal to 475.76, I guess. Okay, we could check that pretty quickly, I guess, if it looks about right. 15 squared is 225 times 25. Okay. That's going to take some work. But there's another shortcut for it to see if I'm about right. In the balance case anyway, in the balance case I can write this out a little bit nicer quite easily. Because what would it be? This is just the I think it comes out like this. Summation yi dot bar minus y double dot bar squared, and then times 5. I goes from 1 to well, this was the number of equal observations, the n, okay, which was the 5 also. This is the n, and this was up to k. All right, let's check that. Well, in the case of in the balance case, because that would have been, let's see, what ni equals to n for all I. All right, let's just see that, because if I expanded this, I'd get, so these are n yi bar squares. If I expand this thing, because the average of the yi dot bars is then y double dot bar. Right? So this is the sum of squared deviations about the mean. The average of the yi dot bars, you just average these 5 numbers, you get 15.04. Right? So, because then this is just, again, the shortcut method. Okay? This should have been the total n, and this was, I'm sorry, there's a different n here. I call this the, yeah, they usually call it I like this. Okay? The number of treatment levels. J goes from 1 to 5. J goes from 1 to capital. Well, I usually call it capital J, I guess, then. Yeah, call this capital J. All right, that's the Ni equals J. J goes from 1 to capital J. Now we're really starting to get there. Now we look like analysis of variance. Okay, so now, because the notation is correct. Anyway, so you can check that. If I take the sum of, if I take 5, then J is 5 now. If I take 5 times the sum of squared, this was my actual n, which was the 25. Okay, that was capital K times capital J. Okay, in this balance case. If I take J equals 5, let's see if that makes sense. I'm going to take this minus 15, this minus 15, this minus 15, this minus 15, this minus 15 square, and add and then multiply by 5. Does that give me 475? Let's see, that's 20. That'll be a 25. 6 is 31. Another 30. 60. And another 15, 16, 16, 75 times 5. That's close enough. 80 times 5. 80, yeah, maybe 85 times 5. Anyway, it's believable. I'm in the ballpark, plus or minus 100. Okay. It's hard to do in your head. Okay. So I think it does work out. Yeah, there was a bigger contribution here. So this is called the between groups sum of squares. And so that gives you a little education in the area of analysis of variance. So this is with the residuals of a thin group sum of squares. This is the between group sum of squares. Okay. Yes, why don't we take a break now? Questions about that? That's sorry about all the notation. They didn't put all this in the book.